Melting point. That's when a solid converts into a liquid. The particles get far enough so that they can slip in between the gaps from one another. And then boiling point, that's just a special case of evaporation. And that's where the water molecules, in this case, are being heated. They quickly move away from each other due to the kinetic energy that they have from the heat, and they form a bubble. Inside that bubble, you will have water molecules get trapped, and then they will escape into the gas phase. There are a few different definitions for boiling. Boiling is based upon the vapor pressure above the liquid. So let me see if I can find these definitions. Here's one. The temperature at which the substance's vapor pressure equals the surrounding air pressure. You know that the higher that you go in the mountains, the lower the vapor pressure. So if you're in the mountains, the atmospheric pressure drops. Think of it as there's less air above you. And then this would cause the boiling point to drop, because it doesn't have to reach as high of a pressure above it to make that liquid boil. Okay, so that other definition for boiling is right here. The highest possible temperature in the liquid state at any given atmospheric pressure. Okay, so the normal boiling point of things happens at sea level. And that's because we are 0 feet above sea level. That's just what they refer to it as. And then I'll show you a diagram of that in a later chapter. And then I think we can go on to, this book is missing pages, that's why. We can go on to the next page and let's talk about volatile substances. Substances that evaporate at really high rates are considered volatile. Don't confuse volatile substances with things that are explosive. It's not the same concept. So this would be things like rubbing alcohol and acetone, which is a nail polish remover. Okay. Volatile substances, there's a lot of them in the gas phase. That's why they have high vapor pressures and they are having low boiling points as well. Okay. Now, a couple of constants that are used when we're converting between the different states of matter would be heat of fusion and heat of vaporization. You will mostly see these abbreviated as a triangle with an H. And then fusion will often say FUS in the lower right-hand corner, and vaporization will often say VAP, okay? You will see these things on heating curves and cooling curves, and let me explain why. The heat of fusion is how much heat it takes to melt something at its melting point, okay? And it's the difference between the potential energy of the solid and liquid states. What's potential energy? Potential energy is stored energy. Typically, it's stored in the bonds. Okay, and so heat of fusion has units of joules per gram, so I can use that as a conversion factor. They normally give you a table with those values for certain substances. Same thing with the heat of vaporization. That's how much heat is required to evaporate something at its boiling point. That's the difference in potential energy between the liquid and the gas state. It also has fraction units, so we can use it as a conversion factor if needed. Now, let's take a look at how you would see this on a heating curve for something. Okay, so if you go on to this heating curve, here I've got my solid ice being heated, here's my liquid water being heated, and here's the water vapor being heated. When the temperature is not constant, that's when the kinetic energy is changing. So in this region, we've got the kinetic energy increasing. Here we do as well. And then we do over here. And that's because the particles are moving more and more when the temperature is increasing. Then you've got your phase changes, which occur when the temperature is constant. So as you're moving from left to right here, we're melting. So the moment that it starts to melt until all of it's melted, the temperature will remain constant. Okay, now heat of fusion applies here within this region because that's the amount of heat it takes for a certain amount of water to melt, to go from ice to liquid. Over here, this is where your heat of vaporization applies. Okay, because you're converting a liquid into a gas. Okay, so you would absorb this heat of fusion and heat of vaporization as you're moving in this direction. So this is the endothermic direction. You have to put heat in to get that to happen. If you were to read this in the reverse direction, going this way, this would be the exothermic direction. You would release the heat of vaporization, converting from gas to liquid, and release the heat of fusion, going from liquid to solid. Does that make sense? Okay. Okay. Is that the last page? No. Okay. One more. Last one. Yes. Okay. So this page just gives you the constants for methane, ammonia, water, and magnesium. You may use this as a reference, especially if you're converting between, oops, wrong one. If you're converting between joules and grams for something, you can use those constants to make that happen. Okay. They talk about reactivity, which is something that we're going to talk more about in AP2. It's not really relevant to us right now. Okay. Any questions for me?
Your heat of formation combustion on those ones? We just have 2 extras.
You have 2 extras? Tell me what they are.
Heat of combustion and heat of formation.
Okay. Heat of combustion is just if you are combusting something, which means you have, let's say, a hydrocarbon reacting with oxygen to produce carbon dioxide and water. That's when you would have the heat of combustion applied. Okay, what was the other one?
Formation.
Heat of formation is when you have pure elements combining to form a compound. So if I have like chlorine gas, just pure chlorine, combining with pure hydrogen gas to make hydrogen chloride, that would be considered the heat of formation. So they have to be pure reactants for that to apply. Good?
Yep.
Awesome. Okay, so let me unlock your homework.